This is Leigh Orf. Came highly recommended by Matt Sikowski. Says he has some eye candy for us today related to these simulations. So Leigh is a scientist at University of Wisconsin-Madison, and that's where he got his PhD in atmospheric science.
That's right. Well, thank you so much. Absolutely. And thanks for the invite. This is kind of cool. I didn't know about this conference, but I like it. I like the location. I like the hot tubs. I like the hot springs. All right, I don't ski much, but if I did, boy, you guys have it made. So, okay, I'm going to cheer it up a bit from our last talk and talk about devastating tornadoes. I have been working on related work to thunderstorms since my PhD work in the 1990s. I studied downbursts, which used to be of great concern for aircraft. They cause wind shear, they can cause aircraft to crash in the landing and takeoff phases of flight. We've pretty much solved the downburst problem by putting Doppler radars at our airports. I then decided if I was going to have a research program, I needed to shift it to something else that was fundable and, of course, intellectually interesting, but also involved in thunderstorms, because that was my background, and it went to supercell. So I started doing supercell research in 2003, and I've come a long way. It's been an interesting ride. I have managed to simulate an entire supercell thunderstorm, multiple resolutions, produce devastating tornadoes. It's related to an actual event that happened May 24th, 2011 in Oklahoma. And I've put a lot of effort into things that are most meteorologists would consider to be absolutely boring and scary, like, well, not scary so much, but how do you animate every single model time step in your simulation? I recently managed to do this, and I'm going to show some of this to you today. In fact, this is some footage that hasn't been seen by anyone but my small research group at this time. So in this image, this cover image here, this is from the highest resolution simulation, I think one of the highest that's ever been conducted on a supercell, 15-meter grid spacing. You've got two tornadoes in this image. The one on the left is an anticyclonic tornado. The one on the right is a cyclonic tornado. You can see features that, if you're familiar with supercells, you see the rain in the rear flank of the storm, you see a tail cloud over here, wall cloud. It all looks pretty good. All right, so what am I trying to do here? Basically, we haven't figured out, and I say we as the scientific community, we haven't really figured out how tornadoes form in supercells, how they're maintained in a supercell, and the biggest one probably is how some supercells produce these devastating tornadoes while the vast majority do not. And you guys are familiar with this kind of issue, right? The most rare event is the most extreme. It's also the one we need to pay the most attention to. So the way I'm approaching this is purely through simulation on supercomputers. I personally am not an observational meteorologist, but I collaborate with people who do go out in the field, because you have to always keep your eye on the real atmosphere in this work. I work at the Space Science and Engineering Center. We have our fingers in the GOES satellites. We do tons of work and research on how to take the data that comes back from the satellites and turn it into stuff that we can use to better understand the atmosphere, better predict, better feed our models to do better predictions from our models as well. And I am doing work purely in simulation, but there's so much potential work to be done to cross over the work I'm doing now with observational work, and I look forward to those opportunities. So anyway, but what I'm doing right now, I simulate these storms on supercomputers. The work I do requires the most powerful computers in the world. I'm using the most powerful computer in the world that I can access, which is called Blue Waters. I've always been very interested in visualization as a method for discovery, as a method of analysis, not just pretty pictures. And I've gotten pretty good at some of these things. We're just getting into the phase of this research where we're quantitatively analyzing things. That means getting the numbers right, putting trajectories in, looking at the forces acting on the different parcels as the storm is getting its thing together. And of course, we have to compare to observed storms, because that's the real world. And again, as I said before, we want to study these storms because they produce the most fatalities. So we're talking EF4, EF5, enhanced Fujita scale. I don't have to describe that to you guys. The Fujita scale was updated in the early 2000s to have more damage indicators. Which this means is when you go out and look at the results or the aftermath of a tornado, there are more indicators to help figure out how strong the winds were that caused the damage. A lot of engineering went into that. And these long path tornadoes, so I'm simulating storms that produce tornadoes around the ground for an hour or more. Obviously, they have more potential to cause damage because of the longer path. And again, we don't really know. We have a lot of indicators in the environment about how important low-level wind shear is, and lots of CAPE, and it's the nature of the wind shear, but we just haven't been able to predict very well. We usually issue our warnings after the tornado's on the ground, or we see a TVS on the radar and we call for a warning, just because it's the safe thing to do, but we have a 75% false alarm rate or something like that. So how do you do this? You need a cloud model. I'm using one developed at NCAR, National Center for Atmospheric Research, which is National Science Foundation funded. The model's called CM1. It's open source. You can download it and run it on your laptop if you want. You probably can't do these simulations, and I'm going to show you on your laptop, though. You need a good set of initial conditions, garbage in, garbage out. I'm using an atmospheric sounding that is basically from a model sounding, but it was the air adjacent to the actual storm that produced an EF5 tornado, the first El Reno tornado, May 24th, 2011. And it works. This was a process that took a lot of trial and error to get to go. Many years of work went into this. A lot of different soundings, a lot of different approaches, different microphysical parameters. If you're familiar with models, there's a lot of knobs that you can tweak. And there's no right or wrong setting on a lot of these knobs. We need this machine like Blue Waters. I'm using, the biggest run I've done so far was on about, 120,000 floating point, no, actually, no, it's more than that. A lot, about half the machine. These numbers get kind of crazy if, we talk about petabytes. 1,000 terabytes, a petabyte. I've made more than 1 petabyte of data from this research. Most of the work that I put in early in this was into just basically preparing myself for this simulation. When models create data, they create an awful lot of data, but getting that data from the memory of the model to the disk is a very challenging process, and I've found some ways to do that are pretty efficient and allow me to do things like save every single model time step during the tornado and visualize that as well. And I just got that part working last week. So I was burning the midnight oil so I could show you guys some cool stuff. And you do need some luck, because a lot of these storms, when you try to simulate a storm, you don't know if it's going to form a storm anymore. We know that 12 hours before the outbreak occurs if we're going to have a tornado in, say, Moore, Oklahoma. Chances are the answer is yes if it's Moore, Oklahoma. They seem to get all the tornadoes. Anyway, so how big is this problem? The 30-meter simulation I'm going to spend most of my time on is 1.8 billion grid cubes. So this is the mesh parameters, 22,000 or 2,200 by 2,200 by 380. I always sort of laugh when I look at the number of vertical layers in most of our operational models, is like 20, 30, 40. I'm getting up to like 800, because you really got to capture the vertical. The supercells are roughly, 20. They're very. The aspect ratio is roughly 1. It's very important that we get the vertical part and the horizontal part right. The biggest simulation I've done has been 18.4 billion grid cubes, and this is getting up to. We're starting to approach the capacity of the Blue Waters machine, but I could probably get down to 10 meters. But at this point, I've got so much great data, I don't know that I really need to. There's so much analysis that I want to do. So the event that I'm simulating is May 24th, 2011. The observed storm produced an EF5 strength tornado. It was on the ground for an hour and a half or so. The model produces a similar type of tornado. It's on the ground for a very long time. We see all sorts of very interesting detail involving non-tornadic vortices that are very prevalent throughout the cold pool of the storm, along the edge of the cold pool, and within the cold pool. And some of these super high temporal resolution imagery that I'm going to show you in a minute, the videos really show how the updraft is tapping vorticity out of the cold pool in ways that I don't think we've ever quite seen before. Our group has identified a feature called the streamwise vorticity current, which is basically air from the cold pool that gets bundled up along the forward flank of the storm, and then the updraft sort of says, I'll take that vorticity and I will draw it up into myself, and it helps to strengthen the updraft at low levels. At least that's our working theory. We haven't done the quantitative work on this, but apparently this SVC thing is what makes this possible. It lowers the updraft very close to the ground, very high velocities near the ground, and when you have this monster updraft extending to a few hundred meters above the ground or so, it's going to suck everything up into it, and when it does that, interesting things happen. Okay, so this is the boring part of my talk. It's going to get more interesting in a minute. But I do want to show some observations first, because we always have to keep our head in the real world, us modeler types, because it can be easy to go down the rabbit hole in the model world without pulling your head out and looking at the real atmosphere. So a lot of work in meteorology, as you guys know, is dedicated to field studies. A lot of it's dedicated to theory and and modeling as well. So before we delve into the simulation data, let's look at some real supercells. So here's a nice example of the type of storm that we're trying to simulate. One of my research collaborators, Bruce Lee, said, hey, this would make a great picture to show because it has a lot of the elements that we see in our simulation. And it's a little dark, but you'll see there's a tornado. In fact, if I just go a little further, I'll do that. So there's our tornado. This is the rear flank of the storm. We're looking probably towards the west or northwest here. Here's a tail cloud. It's kind of dark. The forward flank of the storm, you can see precipitation falling. You can see rain shafts over here. And this is what we consider the mesocyclone, the rotating updraft that's supporting all this action. This is the simulated storm. This is right after I got the simulation to go, I made this image. It's zoomed in a little bit, but you can see the same features that we saw in that other image. Of course, the ground doesn't look kind of pukey green, but that was just the choice I used to. I'm colorblind, by the way. It makes things interesting. Looking at radar is a lot of fun. Inbound, outbound, no, we got to change that color map. So here's our tornado in the simulated model, the tail cloud, forward flank, rear flank. I don't show the rain in this visualization, in this image. But hey, that looks pretty good. I think it looks pretty good. Here's GOES 16, wonderful, wonderful satellite. We can get data every 1 second, or not, sorry, 1 minute. That's GOES 20 maybe. Here's a supercell making its path across. Here's a whole outbreak going on, and this is designed to show you both the wonderful temporal resolution of GOES 16. We can get images every 1 minute, and also I'll pause here. You know, these events tend to be clusters of storms. The storm I'm simulating is an isolated supercell. When you start getting these interactions going on and stuff in the real atmosphere, that greatly complicates things. So keep in mind that my simulation, as realistic as it looks, still does lack a certain amount of noise and stuff that goes on in the real atmosphere. Although the real storm that I'm simulating, 24 May 2011, it did eventually turn into a line and then kind of gust out. But anyway, so GOES 16. I'm repeating this loop over and over again because this is the kind of motion I'm seeing in my simulation. Here's the tail cloud streaming in. You see air streaming in from the right to the left towards the rear flank and rotating. Here's the mesocyclone. And a tornado did not form in this supercell, but it shows a lot of the stuff. Here's the little rain foot that comes along the forward flank. Same basic thing here. Here's the tail cloud streaming in along the forward flank, wrapping around, and this is wraparound process. There's sort of this wrapping that seems to, and it's wrapping already, but there's like this, I'm seeing something happens that sort of makes it almost inevitable for the tornado to form. And that's kind of how I'm looking at this. There's storm scale processes going on in the simulated supercell that make tornadogenesis an inevitability. Rather than looking for a trigger to form a tornado, it seems there's a system of processes going on within the supercell that is creating a tornado-friendly inevitable environment, or tornado-inevitable environment. Okay, so here's the full model domain of the supercell. Again, you've seen this image before, but zoomed in a bit. 120 kilometers on a side, 20 kilometers deep, nice overshooting top. Look at that little tiny tornado. We have to simulate this entire storm at high enough resolution to capture what's going on in that tornado. And inside the tornado, we have to have enough grid points across it so that the sub-vortices that occur within the tornado are being properly resolved. Because these are multiple vortex tornadoes, as you'll see. Here's a cool visualization done by David Bach at the National Center for Supercomputing Applications. This shows the model mesh. We're going to park the cloud on and tilt it up to look underneath it. Here's your overshooting top. He's rendered just the cloud field, but it really does a great job of picking out all the detail, mammatus clouds. You know, you can really see what's going on. This is a really nice way to render a supercell. He's done a great job to pick out some of those features. Most of the time, I'm focusing on just this region right around the tornado. Getting these big views is difficult to do computationally. Okay, so this is some new stuff that's never been shown before. I've managed to save every model time step of this simulation. That's crazy, by the way, just in case you didn't know. This is the cloud, and I'm shading the cloud using volume rendering with vorticity. What that means is these little glowy bits are regions where you want to look at because there's spinning going on. There's some sort of vorticity. So, you know, this is the region to keep your eye on right here. But notice this stuff kind of streaming in from the right to the left. This was the same theme we saw in those video loops I showed, where you have this sort of transport of vorticity along the forward flank of the storm into the region where you basically, the point of occlusion, where the rear and forward flanks kind of come together. So, you know, this is 5 times real time. And some of these videos have so much data, I speed it up a little bit for the sake of time so we get out of here before too late. But notice how, oh wait, what's that guy doing? Little bit of yellow going on. When you start seeing blue, that's the tornado, because I've rendered it such that the blue, the dark blue, is the strongest amount of vorticity. Okay, so our tornado has formed. You just saw it. Now notice how, it's a nice little wall cloud going on here. I mean, it looks pretty darn good. So again, I do this because this is the kind of thing, aside from shading it, that an operational or a field meteorologist would go, oh, okay, I see what's going on here. You've made the model look like the storm, and we can relate on the same plane. All right, so you've just seen tornadogenesis. Looking at the cloud field is not the most useful field to look at, but it is the most visible, literally, what we see. Okay, this is vorticity magnitude shaded by the updraft velocity. So this red region is the updraft. This is like 10 minutes before tornadogenesis. We start with a lot of these linear features, these vortices that sort of just hang out along the border between the environment ahead of the storm and the cold pool that it's producing. Now you start to see the generation of the SVC. And look at all this vorticity. It's gray, it's horizontal, it turns into yellow and red, it's vertical. So this is all being sucked up by the updraft. The updraft is a cold pool, it dines on the cold pool. And this is something that I think hasn't been clear in a lot of our work on supercells, but at least in this simulation, what's going on near the ground, everything is sitting over the cold pool, and everything you see in the low-level mesocyclone is cold pool air. There's a general feeling in meteorology that, well, it's hard to lift warm air because it's harder to lift cold air because it's more dense, and that's true, but there's a lot more to it than that. That's a very linear way of thinking. So here is our tornado. It's doing all sorts of cool stuff. That was an anticyclonic vortex that got slurped up along the tornado. There's a tremendous amount of turbulence. The rear flank of the storm is kicking out all this mess. This is, again, vorticity. Blue means we have vorticity that's sinking. So here's like the vorticity over here in the forward flank. This is where the forward flank downdraft is. The rear flank of this storm actually contains a lot of updraft air. There's no RFD, there's an RFU, a rear flank updraft. Essentially, it's basically the updraft is so powerful and strong, it extends into the rear flank of the storm. To be fair, though, you will see a lot of blue here, and some of these rear flank downdrafts are very shallow and very transient, and I'll show that a little better later. While I've been blabbing on, this thing is just churning. We're out to, it's been on the ground for over an hour now. It is widened, it's a multiple vortex tornado. It's also getting sort of occluded. There's a lot of rain falling. You don't see that in the vorticity. But look at all these horizontal vortices being, lifted up. This stuff has been seen in the field all the time. They call them noodles sometimes in chaser lingo. You see these little horizontal vortices come and go. We're seeing those in our simulation as well. So that's gratifying. That means we're probably getting the physics right, or at least right enough. Because you're never going to get it 100% right, and all models are wrong. They're just different, varying degrees of wrong. All right. So you'll notice there's a downdraft in the center of this tornado. A two-cell tornado has a downdraft in its center and two intertwined vortices that are going on in here. And that will become clear in some future video that I'll show you. But here is where it's starting to decay. You see a whole lot of horizontal vortices here. I think what's happening is you've got basically a big downdraft that kind of overwhelms the tornado, and as it does, it creates shear that creates these vortices, and then it just kind of spreads out. But there's still a tornado in that mess. But at this point, it's getting into its decay phase. It's becoming occluded, it's weakening, it's widening, and the updraft is having to it's so far into the cold pool that there's less of that nice, positively buoyant air to drive it. I think what's going on. But it's pretty. But anyway, this feature here is very important, I think. This is the streamwise vorticity current. So I'm now dropping parcels to show where the air goes, and notice how it follows the vorticity. The cloudy field that you see moves exactly with the wind. That's what we call streamwise vorticity. That means the vorticity, remember vorticity is a vector, velocity is a vector, those two vectors are pointing in the same direction. Streamwise helical flow, like that. Now, the SVC does not encounter a tornado, at least directly, but what I think it's doing, The updraft is super strong right here, and this is helping to make the updraft strong, which is helping to keep everything going to maintain the tornado. And those details need to be worked out. But the visualizations show an awful lot. Okay, this is some really cool new stuff. This is the same vorticity field. I'm shading this one by the vertical component of the wind, this one by the wind speed, and I'm using some slightly different parameters here. You notice it's a little sharper focus here. You're looking into the storm more. I'm going to pause it right here because I just want to show you something. So this is the cold pool, right? Look at these guys. This is horizontal vorticity that the updraft is just saying, okay, I'm going to tilt you. It's just drawing everything. I think it's also forcing the streamized vorticity in the cold pool, so everything gets organized, everything's pointing in the same direction, and then it's lifted. And I think when we start to do budget analysis, we're going to find out that, yeah, that's what's going on. It's all this baroclinicity in the cold pool and the organization of this vorticity that is pretty much leading to a tornado. Now, look at all these vortices. They're almost all cyclonic. There's some antis, but these are mostly cyclonic. Notice how you sort of a little point here where things are kind of coming together. This feature here I'm calling the wraparound feature, at least in my own head. I don't know what I'm going to really call it, but this wraparound aloft, this is a couple kilometers above the ground, seems to always precede tornadogenesis. Once this kind of wraparound occurs, there's our tornado. And eventually, you know, when the tornado actually forms, you have to look at the wind speed, but this vortex that you see now, that's the one. And it's going to continue to grow over time. And again, I want to reiterate, you're seeing every single model time step in this animation, 1/6 of a second. So there's nothing more to be seen in time. You can't show anymore because there isn't anymore. And I'm showing you the full resolution, the spatial resolution as well, but we can still go to higher and higher resolution. And I've already doubled the resolution of this simulation. And got similar and also intriguing results. So this is it. You've seen tornadogenesis in the vorticity field. You've seen it in the cloud field. And I've just recently, as of yesterday, all my simulation work for this, I've done this simulation in chunks. It's based upon an earlier simulation, and I've got it all done. It was about 75 terabytes of data, and I've got it all backed up, so that's good, because I'm going to get years of science out of this simulation. I mean, we can do all sorts of cool stuff when you have every single time step. You've essentially captured the simulation in its entirety in amber. You can take it to any computer you want and now analyze it. So here's another view. This is a view looking east. So this is the streamized vorticity current, which to the best what I can tell is basically the forward flank downdraft boundary consolidating that baroclinically generated horizontal vorticity getting sucked up. Everything goes up. Anything that comes close to the updraft goes up. But there's some sort of feedback because this, by virtue of this SVC, the updraft is getting stronger at lower levels, and it's able to do things like peel vorticity right out of the ground. I mean, it's like it's sucking it out of the cold pool of a straw. When I first saw these, I was just blown away. But really, a lot of research on tornadogenesis has looked for the trigger. We're always looking for the trigger, that downdraft, that RFD surge. I'm looking at this more of a system-wide process thing. In other words, there are storm scale things going on that, in certain cases, with certain orientations, make tornadogenesis inevitable. That is my working theory. It may change, but that's my working theory. I'm going to pause this again. Look at this. I mean, you can't, this is why I visualize. Because I'm going to have to write papers. This is the irony of this. I've got this beautiful thing. It shows everything, but I got to turn it into words as if it doesn't exist and write a paper about it and then show the picture. But I mean, that's the way science works. That's fine. But you can see that vorticity is being tilted, right? We have horizontal vorticity. It's being tilted. There's no better way I know to show it. And there it is. And in other words, the updraft is sucking that vorticity out of the cold pool and turning it into vertical vorticity. Now, then the question is, well, what's the source of the horizontal vorticity? We need to look at the shear profile of the cold pool, all the interesting dynamical things going on in the cold pool. Look at that. You see it. There they are. That's going on in this simulation. I suspect it's probably going on in the real atmosphere. Notice all this green. I'm going to pause it here too because, whoops, no, I'm going to turn the music on. It's just, everything just seems to be converging to that one point. This dark green region indicates the updraft has gotten stronger and stronger. I haven't shown all the annotations here. I didn't have time to put them in. But the story is updraft is getting stronger and stronger. It's getting stronger at low levels. And the SVC is probably facilitating that. And as a result of that stronger low-level updraft, it is slurping vorticity from all quadrants, basically. And that process leads to a tornado in this case. So there's probably just an ideal balance of shear and cape and internal mechanisms going on that lead to this type of event. I spent hours looking at this stuff. And I tell myself I'm doing science, and I think I sort of am. I mean, there's a lot of information in these animations. Okay, so here's a storm scale view. This is the updraft isosurface, red, and blue is downdraft. So if you're an RFD fan, you're looking over here, there's some blue popping up. That's fine. I don't see any RFD action going on for that tornado. It's all coming from the forward flank. It's this accelerating process. There's a little RFD stuff. I'm starting to think of the RFD as more of it's not necessarily forcing things in this simulation, but it's being forced by similar things that are causing other interesting things. So here's our tornado. You know how I told you it's a multiple vortex? I'll pause it again here. First of all, it's still pulling vorticity out of the cold pool. You can see it. It's right there. And watch the tornado. See those two? That's a two-cell tornado. We've seen this in chamber studies, etc. Every model time step, there's a downdraft in the middle of that thing. But all that lovely cyclonic vorticity, red is cyclonic, blue is anticyclonic from a vertical perspective. So this is all, our mesocyclone is all about cyclonic vorticity. Our tornado is primarily about cyclonic vorticity, although you'll see these little anticyclonic vortices sort of kick out from the rear or forward flank and get slurped around the tornado. And there's one animation that just blows my mind that I'll show you in a second. I don't even know what to say about it other than just watch it because it's really cool. But so anyway, this is it. It's the updraft. There's a certain balance of forces at play here. We're able to maintain a very strong low-level updraft, probably due to the SVC, or at least partially due to the SVC. That in turn leads to a low-level updraft that's slurping up vorticity like mad. There's a lot of it in the cold pool, and that leads to our tornado. Here's another beautiful view, just to get your bearings, rear and forward flank, peeling vorticity out of the cold pool. Again, I can just sit here and talk, but I just look at this and go, wow. Every time step, we've got it. It's been saved to disk. I can't wait to get into this data and do more than make these wonderful movies that tell a lot, but they don't tell everything. And we need to figure out, we need to tell a real story here. But this certainly sets the stage quite nicely.
Where's the downdraft? You're doing multiple.
Derek, since I'm shading vorticity, you're not really seeing it in this. So I'm shading vorticity by the vertical component. So it's just not being shown because I'm showing vorticity instead of the updraft. But this stuff out here, we're looking, this is the rear flank. The rear flank tends to produce a lot of, I would call turbulent, primarily anticyclonic vorticity, probably due to the fact you have a downdraft. It should be the opposite sign to some extent than the updraft. Here's the one that I just don't have words for. This is two views of the same thing, but keep your eye on this blue guy. Just follow this thing. And I'll shut up because you just got to see this. So it kind of grew out of the ground. I guess I won't shut up. Makes one turn, and now look at that. It's basically growing out of the ground. And it makes another turn, and up here it's gone around once. It's going to make another turn. This is a coherent vortex. It goes around again. It's anticyclonic. And that's the thing. The anticyclonic vortices do not play well with the cyclonic tornadic vorticity. It's like two magnets, pointing north together. Although, the analogy doesn't really work because in this case, it's the opposite signs that are more pushing against one another. But we're capturing all this. And so, you know how there's cases where, the tornado was heading right for my house and it took a left turn and could have been one of those. Could have been a topographical, could have been a million things, but it could have been that too. Here's from a 20-meter simulation I did. This was sort of designed to look kind of physical. Big nasty tornado. We're looking at rain and cloud here. You can see the multiple vortices. This is now sampled every 1 second, so it's not as smooth as the previous ones. I'm going to share with you, you've probably seen this video before. This poor guy got stuck on the side of I-39 for the Fairdale tornado, and he kind of froze and stayed on the side of the road. He was okay. He was very, very close to the tornado. But notice you see the multiple vortices here. If you look carefully, you'll see some clear sky. There's a clear sky right there. There's some clear sky right there. So you're seeing that this Fairdale tornado is definitely a multiple vortex tornado. Let me see if I can do it one more time. He captures one more right about here. There you go. So there's one of the multiple vortices. We're seeing the same thing. And I show these to say, hey, we're probably on the right path. I mean, yeah, we're on the right path for sure, but as a scientist, I'm very conservative about my science. I'm very nervous about making any grand declarations. Pause for a second here. This is the highest resolution simulation I've done to date, 15 meters. I'm starting out, this is actually an anticyclonic tornado. It lasts for a short period of time before it dissipates and is followed by a cyclonic tornado. And there we go. There is our cyclonic tornado. So now notice the stuff streaming in along the forward flank is a little more cellular, more turbulent. This makes sense. We've increased the resolution. You should be able to get things to be more, if it wants to go that way, we now have the resolution to show it. There's one of those horizontal vortices that went up the tornado. Here's some blasts in the rear flank. I'm going to pause it right here. So I haven't talked about this blue. This is the cold pool. So blue is cold, but there's some warm air in the cold pool as well. And a lot of it's in the rear flank. And a lot of it, notice you have this big rain shaft, right? You typically think of rain falling, evaporating, cooling the air, leading to cooler air, right? Well, what I see here is I see a signal in this cold pool that shows warmer air first, then the rain falls. What the hell is going on? I think this is strongly dynamically forced. It's not being forced by hydrometeors, it's being forced by pressure gradients. So there's a downdraft that's being forced by pressure gradients that's pushing the rain down, basically. But first, some of that air hits the ground and adiabatically compresses and is warmer than the surrounding atmosphere. So you get this warm downdraft full of rain. Crazy. And we need to look at this a lot closer because it's bizarre. But you get these warm surges in the rear flank. There's another one. I'd studied downbursts. This looks backwards, right? You should see cold, not warm, but it's because it's so dynamically forced. This is kind of cool. So it kind of gets rain wrapped for a little bit. So if you're chasing this beast, you're like, oh dear, but got to be really careful. But what's interesting about the 15-meter simulation, and realize for obvious reasons, every simulation is different, even though it's the same environment because of the way the nature of numerical work. But this guy goes and goes. Very interesting baroclinicity here. This very sharp gradient here in the rear flank is interesting. An anticyclonic tornado forms along this gradient. It doesn't really surprise me. There's definitely some horizontal vorticity to be tilted, and you'll watch your eyes right around here. But this looks really good. I mean, this is starting to look more and more vortices going around. It's crazy, crazy. But I'm watching this, and then I see this guy over here, and I go, you got to be kidding me. And here it goes, right in front of your eyes. Anticyclonic. Now, there aren't a whole lot of anticyclonic tornadoes that are observed in nature. And then they do a little dance. It's really kind of cool, actually. But I never would have believed this if I hadn't seen it with my own two eyes. But anyway, anticyclonic tornadoes do occur, and in right-moving cyclonic supercells, they form right where the one that I showed you formed. So even though the observed storm 24 May 2011, I do not believe produced any anticyclonic tornadoes, that's where it should have formed if it was going to. So here's vorticity again. With a 15-meter run, there's a tornado. This one's running really fast. I didn't make as many frames. But the story is, here, I'll slow it down a little bit. There's the demise of the anticyclonic blue guy. Shortly following that, you get the wraparound. You'll see the wraparound right when you start. I can't really even explain what I'm seeing, but there's this real robustness of the rotation that sort of ensconces the updraft to where you get this tornado. It just has to form. Again, I'm basing this all on these movies, so take it all with a large grain of salt. The science hasn't been done yet, at least the really important part. And I love this. This is the same thing looking. You can see that rotation. It's beautiful. If you don't see horizontal vorticity tilting into vertical, I don't know what to do. I'm cross-eyed and colorblind, and I see it. So you should see it. Okay, so some sort of parting thoughts. I guess you can do this now. This is cutting edge stuff. This represents the leading edge of what's being done. So this is gratifying that I'm able to do this. I want other researchers, I'm hoping other researchers will start pushing the resolution higher because there's some details that we just don't see unless you get up to those higher resolutions. While I'm sitting on this huge pile of data and I'm working to build a research team to analyze it, we're already working on different storms. I want to start doing like Joplin, Tuscaloosa, Fairdale. There's other storms that I want to use the same approach to simulate to see if things like the SVC and this tilting of the vorticity from the cold pool, are those commonalities in these top-end storms? Because that's what we're trying to figure out. What's going on in the top-end storms is not going on in the more common lower-end storms. And as far as for you guys, this is kind of a downplaying statement maybe, but I do really think this is exciting, we're learning a lot, but it will probably be years before this sort of filters up to where it actually assists you guys in, say, issuing more, or, well, you guys don't issue the warnings, but the forecasting community will be able to someday, hopefully, use some of this work to make the false alarm rate go down a bit. That would be one thing I'd like to see. The other thing is where we'd be able to forecast whether it's going to be a top-end storm like I'm showing you, or maybe a more transient EF0 type situation, because those don't kill as many people or cause as much damage. So I think that's where we're going, and I think that's all I've got. Oh, acknowledgements. I want to acknowledge my collaborators. Kathy Finley at St. Louis University, Bruce Lee, he has an LLC. Robert Wilhelmson, retired, University of Illinois. My grad students, Austin Dixon, Kelton Halbert, both from OU. This is all sponsored by the National Science Foundation. Your tax dollars at work. I say that with a straight face. I think we're at a time right now where government spending is looked on very unfavorably, but I couldn't have done any of this without government spending. And I'm happy to say that to anyone who wants to listen. The National Science Foundation is a wonderful thing, and believe me, I'm a little nervous when the government shuts down and I can't submit grants because Fastlane's gone. It makes me crazy. And there's a lot of more even serious things that go on in these shutdowns. But anyway, yay NSF, and I hope to get more of this funding to do more of this work. Blue Waters was NSF funded, and I'm NSF funded as well. So anyway, the talk is online. I can give you a link. I post all my talks on my website. I basically have a YouTube channel. If you want to subscribe, go nuts. Every so often, I will post this talk with audio on that site in a couple days. So I will be happy to take any questions.
Leigh, how big is the SVC, and is it exclusive to the forward flank?
That's a good question. What I am calling the SVC. Yeah, so here's the scale. This is 500 meters. So you can kind of think this is about 1 kilometer or so, at least the way I'm looking at it. So yeah, is it exclusive to the forward flank? I would say that the way we've defined it, it is by definition, because we're the ones who came up with the term. But I would say there are streamwise vorticity currents, like lowercase letters. All these little guys in the cold pool, I'm pretty sure are streamwise. I've looked at the cold pool pretty closely, and this is probably streamwise vorticity, little vortices that are breaking down into individual cells that are then getting lifted in. These guys are only like a couple 100 meters across. I mean, the folks who go out in radars, the folks who go out and observe storms, if they're going to see this stuff, they're going to have to be close to the nastiest part of the storm, because you need to be, you can see into the cold pool and the precipitation as long as you got reflectors back here. The in situ guys, if you're going to deploy stuff, you're in a very dangerous part of the storm. If we're going to observe these vortices in the cold pool, it's going to be a challenge, but I hope that if this work helps that happen, I'm glad, because I think this is probably not just this one storm, in other words. But anyway, I drifted away from your question. But yeah, the SVC, as we're defining, it's about 1 kilometer or so in diameter, but as you see, it's made up of individual vortices. It's kind of.
Do you think the size matters in tornadogenesis?
I would say maybe the size is the wrong word. I would say something like a vorticity flux, something like that. So because you could perhaps have an intensely small SVC or maybe a larger, more lazy SVC, I don't know yet. This is the first time we've seen anything that looks like this in this kind of detail. So I've only simulated this environment in different parameters, but the SVC always looks about the same, although you'll notice in the 15-meter run it's a lot more turbulent. So it depends on how you define it, but I would say what you see here is about what we got.
Were you kind of surprised with, I thought the RFD was kind of interesting with almost what seemed to be the lack of cold air. Was that something that kind of caught you off guard? Or?
Yeah. When I first gave this talk, I didn't know what to say. I feel like I'm at the altar of people who have been studying this a lot longer than I have. And again, I think, I think that in many storms, the downdraft kicks off the tornado. Here, this is a good one to show. The one with I think it happens in many storms. Let me put it that way. It just, not in this one. I can't find there we go. I keep skipping over it. So yeah, so like look in here. Look for one of those warm surges that hits the ground. So yeah, so here's downdraft air, Shoot, I didn't go far enough. But it is very interesting. What's going on in the RFD, to me, it looks more like it's along for the ride more than anything else. And that's what the movies kind of show, right? I mean, that's why I'm saying, I'm just talking about what the movies are showing. I'm not like pulling this out of thin air. What appears to be happening is this intensification of the low-level updraft that results in a feedback process that draws vorticity out of the cold pool, reorganizes it and tilts it and concentrates it to form a tornado. So there's Leigh Orf tornadogenesis in a sentence, sort of, at least where we're at right now, okay? The SVC seems to play the important role of making that low-level updraft so intense. Without the low-level updraft being so intense, you can't get that vorticity flux, or whatever you want to call it, the slurping of the streamwise vorticity effect to get enough vorticity to maintain a tornado. Remember, well, I shouldn't say remember, but since the tornado is parked in the cold pool, all of the air in the tornado is from the cold pool. So if you're just doing a conservation study, you got to get that vorticity from somewhere. It's like the cold pool vorticity is simply being shrunk and concentrated into a tornado. I mean, that's what it kind of shows. It's crazy. It's new. It's weird. You know, that's how these things go sometimes. So that's what this simulation is saying. I want to reiterate though, we're only studying the top end storms. I suspect that in probably more than half of supercells that produce like EF0s, EF1s, chances are there is some sort of maybe a downdraft that leads to convergence, that leads to a spin up, that leads to a tornado. But that would be a genesis mechanism, but it's not a maintenance mechanism. I see no way for sporadic downdrafts in the rear flank of the storm to be able to maintain any sort of tornado. Because it's one thing to create it, but it's another thing to maintain it. So for your typical tornadoes, last 5 minutes, that sort of thing, chances are that mechanism is at play. It's likely that mechanism is at play. I suspect there's also things going on in the rear, the forward flank that are important. But I'm speculating. All I know, I can talk to you pretty intelligently about my simulation, but not every other supercell is my simulation. So keep that in mind. I do not want to generalize. As a scientist, that's a dangerous thing to do. But I will say this is compelling. We got one storm that looks pretty good, and chances are mechanisms like this are at play in other top-end storms, but we haven't shown that yet. Derek.
So, and a comment and a question, like operationally, putting this into working practice, it's going to be a major mind shift for meteorologists to think as an SVC indicator versus a trigger indicator, which is, that'll be a big mind shift. I think. And,
yes.
And then the question I have is, how long in your simulation of this particular supercell was the SVC prominent before a tornado actually occurred?
Excellent question. It's, I would say about, see, the funny thing is, and I'm not trying to dodge your question, is that when does this sort of, so this is the one where I go back the earliest. So right about here, this is this is early on. Before the tornado, right, we've got just a bunch of little icky little know-nothing vortices here or whatnot. Is there an SVC in this image? Okay, well, you do have vorticity here that's being tilted into the vertical, but is it really organized yet? I don't know. Let's go on a little further and see if we can snap our fingers when the SVC forms. And again, I'm doing it all from looking at these images. We're going to have to come down, if we're going to come down with a more refined definition there, I'd say we're sort of in SVC territory now, because now you sort of have a bundle of vorticity and you can see the rotation. But so so if there's an SVC now, we're still about 5 to 10 minutes before tornadogenesis. So I know where you're going with this. What if you could use the SVC as a predictor then the question is, how the hell do you see it on radar? It's not something that's just in that is for our scans to show a nice little couplet. It needs to be like this. But how do you see this? This is horizontally oriented. So, and yes, there are usually reflectors here. It's usually not heavy though. So to see the SVC, that's a question that maybe, talk to the radar meteorologists on that. There's already some work being done in this area. I know people are already looking at this work and starting to look at maybe how we can detect these things, how we can, and some work has been done. Maybe RHI scans. I mean, research radar, I'm sure we could get people deployed to see it. Our WSR 88Ds, not so sure. So, but if in the future there's a way, first of all, if I'm right, if this is actually an important thing, and if we can measure it, we can detect it before, then it would serve as maybe a 10-minute thing. Maybe say, hey, indications are this is going to produce a top-end tornado. We should be especially concerned about this supercell. This is the kind of thing I'd like to see our field go towards, rather than just tornado warning, no tornado warning. You know, yes, no, binary, something a little more refined. Now we do have PDSs and stuff like that, particularly dangerous situations. There's language that comes out that sort of addresses this in a small way, but I'd like to. My goal is this work leads to much more refined forecasts for severe outbreaks. That would be 10, 20 years from now, maybe. Though I really do think it's going to take that long to get there, but I think we'll get there.
I mean, ADDs are going to miss all that low level.
It's too low. It's too close to the ground.
Eventually, we could observe that via satellite.
Oh God, you'd have to use like microwave. How would you see through all the cloud and rain? I mean, you would see the overshooting top, and the anvil takes up most of the visible. The infrared, you're seeing the cloud. You have to see through the cloud. So this would require. And again, what are you going to look for? We don't have Doppler radar from space. You know, we've got I mean, I work for the SVC. We do satellites like nobody does. We're crazy, algorithmic-wise. You know, designing instrumentation, the ABI, all that good stuff. And this is the kind of question I'm going to pose to them. I'm going to say, hey guys, I think this is real. How do we go find it? How do we use satellite technology to detect it, or maybe indirectly detect it? The same thing I'd say to the radar meteorologist. Maybe, you know, how do we do that? And it's going to just take some more basic research before we get even closer to closing in on that. I need to get more storms that produce these, and people need to go out and look at storms and look at the cold pool, I would say more carefully, to look at what's going on. It's just going to be a real challenge, because even though this everything happens fast in a supercell, and capturing it while it's happening is a real challenge.
And you said it's 1/6 of a second?
What I'm showing you, when I split up the model time step, and this is just one of those boring mathematical things, if you're going to run at high resolution, you got to run in smaller temporal increments. This is a stability criterion. The 1/6 of a second is only really a big deal to someone like me who's a modeler, because I've managed to save all the time steps. We're not going to need to scan every 1/6 of a second or anything like that. Our strategies now, we're getting some better radars. Phased array radar is something that's on my radar, as being very important. It can sweep through the storm much faster. If we can do dual radar with that mechanism and maybe an RHI at the same time, you can just scan the crap out of a storm and hopefully capture some of these things. But again, I'm not a field meteorologist, and I don't want to even pretend to understand all the challenge. Well, I understand some of the challenges, but not personally. But I'm thinking in my mind, that's what it's going to take. Some really fast, high frequency scanning radars positioned in certain places to capture this. And that's just the science side. Again, filtering it up to the operational world and the forecasting world, I don't know. I suspect at some point we're going to replace our WSR 88Ds. I mean, they're now dual pole, which is great, but what's the next step? I don't know. I remember when I was in grad school, the WSR 88Ds were coming out. It's a big deal, and we've made improvements to them, but for stuff like this, I just don't know. I don't know what to tell you. Maybe a lot of lower, maybe an array. They tried this in Oklahoma. Kelvin Drogemeyer had a project where he wanted to put radars on cell phone towers and just basically cover the whole area with lots of overlapping radars. That sort of approach would be great. Again, you need high temporal and high spatial sampling for this stuff. Our typical, plan view of supercell, 1 minute later, plan view of supercell, plan view of supercell, junk, junk, junk. It's very chunky. It's very, you're missing so much detail. And not to knock radar, because it's still amazing that we can do what we can do, but the kind of detail we need really, really sensitive radars and multiple radars.
Where are you getting all your initial observations for the storm?
Sure. For this particular case, a RUC forecast sounding. So the rapid update cycle model has been replaced by the RAP model. I forget what RAP stands for. So it's one of our operational models. Again, your tax dollars at work. Lou Wicker at the University of Oklahoma said, hey, try this sounding out, because he knew what I was trying to do. It's a 1 hour RUC forecast off the right flank of the storm that formed. So I'm looking at our models that we run at NCEP and everything, I'm looking at the analysis files or the forecast files. You can get them, some of them. And then I'm doing things like running Worf to sort of get more resolution. But essentially, to answer your question, it was the RUC model. I got a RUC sounding. And I'm looking at RAP, I'm looking at HRRR, high resolution rapid refresh data. So all of the new models that are sort of designed to do forecasting, they're getting better. They're getting better at assimilating radar and other things. They're getting higher resolution. And when an outbreak occurs, they capture the environment pretty well. So I'll go and pluck out sounding and see if I can get a big storm to form. That's my plan for previous and future storms. I'm not going out and launching weather balloons, though. And to be quite serious, I've tried that. I've tried using radiosonde to initialize the model. I'll get a supercell, but I don't get tornadoes. Part of the problem, I think, is that it takes a friggin' hour for the balloon to get to the tropopause, right? It's like 45 minutes. Remember we're on Beaver Island watching weather balloons? It takes a long time for that darn balloon to make it. So you're capturing a time-smeared, spatial smeared profile of the atmosphere because the balloon's also getting advected. So a model sounding is instantaneous. It's balanced. You just pluck it out and you can feed it right into the model, and it probably more faithfully captures the true vertical profile of the surrounding atmosphere because it's instantaneous. It's model data. We've already assimilated some of those balloons into there, but you want to go to the model data to initialize the next model.
So the drones they're trying to create to do soundings, would that help in creating a faster representation of the atmosphere?
Yes, there is some in situ technology with drones and UAVs that I think is very promising. I also know that there's some work being done at Penn State with sort of launching neutrally buoyant balloons and just having them float into the storm. So yes, there are creative technologies I think we can exploit. Miniaturization, cheapening of electronics, and do some things like that. So either launch balloons into there, fly a drone or a UAV, sampling some of the storm. Each of those technologies has its own challenges. I mean, a large hailstone will knock out your plane, right? Or your drone. So I don't know how that's all going to flesh out, but I'm pretty encouraged by what I've seen in some of the talks I've seen where they're deploying armies of drones to go out and do vertical profiles and capture. That is definitely better, or it's a promising technology. Let me just put it that way. I'm liking what I'm seeing when I see stuff like that. And definitely sampling the lower atmosphere is as good as we can.
Good. Thanks, Leigh.
All right, you're welcome. Thank you.